Hello and welcome to this video for the 2022 Level 3 Mechanics Standard for NCA. So we'll get straight into it. So question 1, we'll look at rotational motion at the playground. So some children are playing on a roundabout and Riley pushes the roundabout and gets it spinning at a constant angular speed and makes one revolution in 1.23 seconds. So we want to show that the angular velocity of the roundabout is 5.11 radians per second. So for this question, we'll just note down that it takes 1.23 seconds to make one revolution. So the period is 1.23 seconds. And we know it's a period because the period refers to how long does it take to make one revolution, and the frequency is how many revolutions in 1 second. So it's directly opposite of each other. So we know that the period is 1.23 seconds, and we know that the angular velocity is equal to 2 pi f, and it's also equal to 2 pi over t. So this will just be 2 pi over 1.23, and that should be equal to 5.11 radians per second. And this is achieved level question. So if you can get the correct answer here, that will be an achieved grade for that question. So question B, so Riley stops pushing and 30 seconds later, the roundabout has slowed and it takes 2.04 seconds to make one revolution. The roundabout can be approximated to a spinning disk with a rotational inertia of 57.6 kilograms meters squared. So we have two parts. We want to determine the average angular deceleration of the roundabout as it slows, and we want to calculate the average frictional torque acting on the roundabout as it slows. So let's start off with part 1. So for the average angular deceleration, we'll just look at the initial angular velocity and the final angular velocity and how long it took for that change to occur. So in this case, we know that the initial angular velocity was 5.11 radians per second. So initially, we were at 5.11 radians per second. And we know that afterwards, it's going to take 2.04 seconds to make one revolution. So our final angular velocity will be equal to 2 pi times f again, which is 2 pi over t, and that's equal to 2 pi over 2.04, and that equals to about 3.08 radians per second. And the average angular deceleration will just be the final minus the initial over how long it took for that change to occur. So we have the final minus the initial over t. So in this case, we have 3.08 minus 5.11 divided by 30 seconds. And that should give us an answer of negative 0.0677 radians per second squared. And that will be the part 1 completed. So we determined the average angular deceleration. And now we want to calculate the average frictional torque. So we know that the torque is equal to the rotational inertia multiplied by the angular acceleration. So in this case, we will have torque equals to the rotational inertia, which is 57.6, multiplied by 0.0677, which is equal to 3.9 Newton meters. So that would be the average frictional torque acting on the roundabout, and this would be a merit level question if you can get the correct final answer. So it would be merit if you can get up to here. And for an achieved correct angular acceleration or correct equation, so if you can get the correct angular acceleration, so up to this step here, you will get an achieved grade there. Alright, so for part C, we have 4 friends are riding on the roundabout and in the following position. So they seem to be on the outside of the roundabout. Look at the question C. So explain using physics principles what the friends can do to make the roundabout speed up while staying on the platform. So in this case, we have all of the friends on the outside. So we have more weight of the system is just distributed further distance away from the center of mass or center of rotation, in other words. So if the children move closer to the center, that means more mass will be distributed closer to the center of rotation, which will decrease the rotational inertia of the system. And since the process of the children moving in towards the center does not exert any external torques on the system, this means that the angular momentum of the system is conserved. So therefore, with a decrease of rotational inertia, with the momentum staying the same, we should expect the roundabout to increase in the speed, in the angular velocity. So basically, to start off, we'll say that the friends can move closer to the center of the roundabout, allowing more mass of the system to be distributed closer to okay, so now we talked that the angular momentum is conserved. So since there are no external torques acting on the system, the angular momentum is conserved. Angular momentum is conserved. I should probably add in that when more mass is distributed closer to the center of rotation, that the rotational inertia of the system decreases. So maybe just a side note here, rotational inertia of system decreases. Well, you can use the formula I equals to mr squared. So I is proportional to r squared, which is the distance from the center of rotation. So since a decrease in r will decrease the rotational inertia. So the angular momentum is conserved. Therefore, since the angular momentum is given by the rotational inertia of the system multiplied by its angular velocity, we know that the angular velocity must increase. Okay, and that's it for this question, and this would be I believe it is. Yeah, this is an excellence level question. So there's a couple of points you need to mention here. So first of all, you need to mention that the friends are moving towards the middle of the table. They're reducing the distance from the axis rotation or the center of rotation, same thing. Therefore, the total rotational inertia of the roundabout or the system decreases as more mass is distributed closer to a rotational axis. And since there are no external torques acting on the system, the angular momentum is conserved. And we need to know that L, the angular momentum, equals to rotational inertia multiplied by angular velocity. So the angular velocity must increase. So those are the 3 points you need to mention. And if you mention all 3 of them, should be getting an excellence level grade for this question. So that's all 3 points mentioned. And if you can justify a decrease in the rotational inertia, that should be enough for a merit. And if you just state that the friends should move towards the middle, and that should be you should be looking at an achieved grade for that. Okay, so let's look at question D. So Matilda wants to run and jump onto the initially stationary roundabout and holding onto the poles A and B to make it spin as fast as possible. She tries different jumps on the roundabout. So we're looking at she might be jumping at point A or point B. So assuming that she jumps at the same speed, explain which jump at A or B will make the roundabout go faster. So in this case, since Matilda is going at the same speed, we'll just make an assumption that the amount of force that she exerts on the roundabout is the exact same for the both jumps on A and B. But we notice that the roundabout will have a center of rotation around, we'll just say around the center of the roundabout. And notice that in terms of looking at the perpendicular distance from A and the perpendicular distance from B, we see that the perpendicular distance from point A is actually bigger than the perpendicular distance from point B. And we know that since there's a higher perpendicular distance, that means there will be there'll be a larger torque exerted on the roundabout, since torque equals to the force times the perpendicular distance. So in this case, the distance is perpendicular to the center of rotation. So as I said, the perpendicular distance to A is greater than that of B. So when Matilda jumps, that same force exerts a greater torque at point A. So therefore, we can expect the roundabout to speed up to a greater speed. So therefore, we should first we should link that to a greater angular acceleration, which links to a higher final angular velocity. Okay, so jumps at A or B. So we'll assume that she exerts the same force on the roundabout. However, the perpendicular distance to point A from the center of rotation of the roundabout is higher at point A. Well, in fact, it's at the maximum at point A, so it's higher at point A compared to point B. And we know that torque is equal to the force times the perpendicular distance. So therefore, we expect a greater torque. So we expect a greater torque, and we know that torque is equal to I times of A, not necessarily I times of the angular acceleration. So in this case, we expect the angular acceleration to be greater. We expect the angular acceleration to be greater. Therefore, maybe we should say torque proportional to angular acceleration. Therefore, we expect the roundabout to reach a greater speed for the system. Okay. Alright, so that should be all the points we need to cover for part I. And we'll move to part II first, since the grading for this question depends on both parts. So Matilda subsequently lets go of the pole and slips off the roundabout. We'll discuss the possible effects on the speed of the roundabout and assume there's no friction. So when you see negligible friction, that just tells you this. So some key words here. So that means no. We can just assume no external torques on the system. Okay, so when Matilda lets go of the pole, initially we'll have the total angular momentum of the system, which will be equal to some angular momentum that's part of Matilda, and there'll be some angular momentum that's a part of the roundabout. Then the sum of those will be equal to the total angular momentum of the system. And in this case, the amount of angular momentum that each component has will result in both of them having the same angular velocity. And you can imagine that to be the case, because if Matilda and the roundabout were not traveling at the same angular velocity, we would expect there to be some sort of accident that might be happening there, where Matilda might just fall over since they're not traveling at the same angular velocity. So the roundabout and Matilda will be having the same angular velocity, but they might have different angular momentums, and the sum of those will be equal to the total angular momentum of the system. So when Matilda slips off the roundabout, since we're assuming there's no friction between Matilda and the roundabout, that means we're assuming that there's no external torques being applied on the system. That means that some component of that angular momentum is going to be maintained when Matilda leaves the roundabout, and therefore there's going to be no significant effect on the angular momentum of the roundabout, since remember for the total angular momentum of the system was some angular momentum of the roundabout added to some component of angular momentum of Matilda. So when Matilda falls off, that angular momentum of Matilda is also goes with Matilda, so she maintains that same angular momentum and the same angular velocity, since we are assuming that there's no external torques being applied on the system. And as we said before, Matilda and the roundabout were traveling at some angular velocity that was the same for both of them. So therefore, after she falls off, there will be no change to the angular velocity of the roundabout. All right, so I can't spell, sorry. System. In the system, the total momentum, in the system, the total angular momentum is the component of Matilda added to that of the So say some L total is equal to some angular momentum of Matilda added to some angular momentum of that roundabout. Okay. So well, not jumps off, maybe let's go. We assume no friction, so therefore no external torques on the system. So Matilda maintains the same angular, so Matilda retains the same, we'll call it Lm when she lets go. So therefore, both the roundabout and Matilda were traveling at a common angular velocity. Traveling at the same angular velocity, so when she falls off, she does not affect the component of the angular momentum of the roundabout, so it does not affect our R. So therefore, the roundabout maintains the angular velocity, or just some angular velocity that we're initially traveling at. So the maintains that same angular velocity. Okay, and that's about all we need to really be saying for this question. So looking at both of these parts combined will get you an excellence grade. So what you really need to be saying, so for part I, you need to mention that assuming that applied force is the same, so basically assuming that Matilda traveling at the same speed applies the same force on the roundabout, The perpendicular distance to the center of rotation is larger at A. So remember, we're talking about the perpendicular distance, which will exert a greater torque on the roundabout. So we talk about greater torque, and then hence a greater torque will imply that there's a greater angular acceleration. So therefore, the angular velocity will be higher. So that's the parts you need to mention for part I. And for part II, you need to be talking about how Matilda does not exert any torques onto the roundabout component. So therefore, the component of momentum of the roundabout stays the same. And since there are no external torques on the system, therefore, the roundabout maintains the same angular velocity as it was traveling at when Matilda was still on the roundabout. And if you just mention all these general points here, you should be getting an excellence grade for both those points combined. If you complete explanation for either part I or part II will get you a merit. So either of those will get you a merit. And if you just identify some reasoning, so for example, for I, if you just identify some kind of like just greater torque at A and not really explaining that in detail, you might be able to get an achieved grade for this question. Okay. Question 2, we're looking at collisions in space. So comets and asteroids are loosely formed objects that are easily broken up, especially when they collide. So in this scenario, a 100 kilogram object is moving at a velocity of 500 meters per second, and it collides with a stationary 300 kilogram object. So calculate the distance of the center of mass of the system from the 300 kilogram object when the objects are 4,000 meters apart. Okay, so for this question, we're going to be choosing a reference point, and I always recommend that when you choose a reference point, you should always choose like from what the question is asking. So technically, you can choose like any arbitrary point. Like you can choose a point. You can just say this point here is going to be my reference point, and that's actually totally okay for the calculation, since you just need to shift the final answer by whatever distance that your initial reference point was at. But that just involves more steps, and it's much more likely you will make mistakes. So the question is asking you like how far from the 300 kilogram object when these objects are 4,000 meters apart. So to make things really easy, we're just going to choose the reference point to be from that 300 kilogram object. So for x, for the center of mass, we know that's m1 x1 plus m2 x2 plus however many objects in the system, but in this case it's only 2, so divided by m1 plus m2. So in this case, if we're looking at m1, so that will be, in this case we can say m1 is equal to the 300 kilogram object and m2 is the 100 kilogram object. So this will be 300 multiplied by how much distance away is it from our reference point, which is 0, since our reference point is at that object, so that will be a 0, plus of 100 multiplied by this distance away from our reference point, which is 4 times 10 to the power 3, all divided by the total mass of two objects, which is 400. So therefore, this will be equal to 4 times 10 to the power 3 divided by 400. This should be equal to 10 to the power 5. We're at 1,000 meters. So 1,000 meters should be our final answer for this question. So it should be, if you're looking on the diagram, should be somewhere. So that would be our x, somewhere there. And to do a sanity check of your answer, we see that the 300 kilogram object is much larger than the 100 kilogram object. So we expect the center of mass of the system to be closer to that of the larger object. So in this case, our sanity check does check out, and we should be reasonably happy with our answer here. So correct answer here is an achieved. Okay. So calculate the gravitational force between the two objects when their center of masses are 10 meters apart. So we know that F equals to some G, constant, multiplied by, M over M over R squared. And we know that G is a constant and is equal to 6.67 times 10 to the power of negative 11. So in this case, this will be 6.67 times 10 to the power of negative 11 multiplied by the two masses. So we have what was it? It was 300 by 100, all divided by the distance between the center of masses, which in this case is 10 meters, so 10 squared. And this would be equal to 2 times 10 to the power of negative 8 newtons. So that would be the gravitational force between the two objects. And for part II, we need to find the acceleration of the 100 kilogram object at this separation. And we try to determine whether or not the assumption that the velocities are constant is valid. Okay. So for this question, I'm just going to be doing a force equals to some mass times acceleration. So therefore, 2 times 10 to the power of negative 8, so that's the force on exerted onto the 100 kilogram object, and it's also exerted on the 300 kilogram object. They're attracted to each other, so there'll be a component of force on both of them. So this will be equal to the mass, which is 100 multiplied by some acceleration. So acceleration would be 2 times 10 to the power of negative 8 divided by 100. And that's 2 times 10 to the power of negative 10 meters per second squared. And that is a very small number, so that's 0 with 9 zeros following there. So that's a very, very small acceleration. So A is extremely small. Hence, the assumption is valid. Okay, and for this question, if you can get both of the correct answer, so 2 times 10 to the power of negative 10, and the correct force, that will be a merit level grade. And if you only get the correct force, then you'll get, so this part here, that itself isn't achieved. Okay, so objects collide with no external forces. So again, very key words you're looking at here. So no external forces. That basically just implies that there are no external forces on the system. So it basically tells you there's no external forces. And there's forming 2 rocks, A and B, each with a mass of 200 kilograms. 200 kilograms. These move away from each other as shown in the diagram, in directions of 20 degrees of either side of the initial direction of the impacting rock. So we can show that the size of the momentum at A and B are the same, even though they are in different directions. Alright, so to justify that they're the same, so we know about this vertical component here. This will be we'll just call it some V vertical component. And this vertical component must be the same in magnitude because they're the same in magnitude because the original initial momentum is horizontal, so there's no vertical component for initially. So since there's a conservation of momentum, there's no vertical component after the collision either. So therefore, those two will be the same, but same magnitude, but in opposite directions. So overall, they'll cancel out and it'll be conserving the momentum overall. And we know that the angle here, 20 degrees and 20 degrees is the same. And we know that the vertical components are the same. So we justified that the horizontal component must also be the same. So therefore, the overall momentum or the overall size of the momentum will be different. But obviously, as you can see, the directions are not the same. So momentum has both size and direction. So the size is the same, but the directions are not the same. All right, so you can just say briefly, there's nothing too much to be said here in my opinion. So we could just say like initially, so there's no vertical component of momentum, Hence, after the 2 rocks will have equal momentums, but in opposite directions. We'll have equal vertical component of momentum, but in opposite directions. And that's directly due to the conservation of momentum. So due to conservation, that's just going to say COM, so conservation of momentum. So therefore, horizontal component is the same. Horizontal component is the same since same angle. Hence the overall. I shouldn't say overall. We should say hence the magnitude is the same. It's the magnitude of momentum is the same for both rocks. Same for both. Yeah, that's all we really need to say here. So it's not. I don't think there was too much to be said there, since it should be fairly obvious that they should be having the same size of the momentum. So that will be our answer there. And yeah, this is a merit level question, and this actually they've actually laid out multiple ways you can do this question. So you can use what I've said here, just some basic justification of the same vertical and the same horizontal, or you can just use algebraic proof or calculation. So basically, just use the cosine rule here, and you'll get the same answer. So you can also use some calculations here to justify they're the same. And yeah, so basically the same, or you can just say the same angle to a horizontal, and them and not that one, and we know that the initial momentum component is the same for both of those vectors, so therefore it's the same. So you can also use that to justify. Okay, so for question D, we calculate the speed of the rocks of A and B and use the space below for vector diagrams. Okay, so for this question, we're just going to be looking at the initial momentums. The initial momentum was some horizontal component, and then we'll have afterwards, so this will be PF will be the sum of this, and will be the sum of A and B. So A plus B, so initial some PF, some vector PF is equal to some vector of A plus some vector of B. So in this case, we're assuming conservation of momentum. So the vector addition of A and B should be equal to the original component of the momentum. So in this case, we'll have a triangle, something like this. I think this one, which one was A and which one was B? Okay. This one will be A, and this will be B. And we know from the diagram that this angle here from the horizontal is 20 degrees. And this will be some PI, this will be some A, this will be some B. And like we said before, we're using PI, the initial momentum, is equal to the final momentum, which is the final momentum is equal to some momentum of A plus some momentum of B. And remember, they're vector quantities, so they have both size and direction. So we can calculate the magnitude of PI using P equals to mv. So PI equals to sum m times v, which was equal to something. Sorry, I'm just trying to find the part where they tell me how fast it was moving. Yeah, okay, yeah, here it is. Yeah, sorry. Yeah, they were a little bit unclear with the numbers here, but we have 500 meters per second and 100 kilograms. Apologies for that. So we have 500 multiplied by 100, which is 50,000 kilograms meters per second. So that's the initial momentum, and we know that this will be equal to the addition of the momentum of A plus the momentum of B in this vector diagram. So in this case, there's quite a couple of ways you can solve this. So I'll show you two approaches you can solve this one. So we can use approach A. We'll use the cosine rule. And from maths, the cosine rule is c squared equals to a squared plus b squared minus 2ab cos of c. So for a general triangle here, I'll just demonstrate here. So if we have an angle of big C here, this will be the edge of small c, and we have the two edges of A and B. So this will be the cosine rule, c squared equals to a squared plus b squared minus 2ab cosine of c. For this question, we say that we know that some momentum of B, so we just say some momentum of B, so we say B squared, that is equal to the initial momentum, which is 50,000 squared, plus some momentum of A squared minus 2 times of A times of 50,000 times of cosine of 20. And right now, it's not really solvable right now because we have two variables, A and B, and we only have one equation. But we noticed that, remember that the magnitude of the momentum for A and B are the same. Remember we proved that in the previous part of the question. So the magnitude of A, so we know A and B are vector quantities. So if we look at just the magnitude, so magnitude of A is equal to magnitude of B. So we can just say that A equals to B here. So B squared equals 2. And we can say that A equals to B here is because here we're just worried about the length of the sides, in the other case the magnitude. So here everything is a magnitude, so we can just say that A equals to B. Just keep that in mind. So 50,000 squared plus another B squared minus 2B times 50,000 times cos of 20. Okay, that cancels out. So we have 100,000 times of B cos of 20. That equals to 50,000 squared. So therefore, B equals to 50,000, 50 divided by 100,000 cosine of 20. And that would be the momentum of B. So that would be that component there. So maybe a calculator would do me good here. Sorry, give me a moment. So we have, and just remember, just be careful when you're using calculators. For the mechanics standard, you both have to use calculator in degrees mode, and you will have to use your calculator in the radians mode. So just be extra careful on what mode your calculator is on at all times. Depending on the context of the question, you might have to use degrees, or you might have to use radians. So just keep that one in mind. So this is equal to 26,604.4 kg/ms per second. And for the speed, we just need to divide by the mass. So as you know, P equals to mv. So the velocity or the speed is just this divided by 200. I think it was 200. Yeah. Okay. So that's 133. So it's 133 meters per second. That's our answer here. And alternatively, you can, instead of using the cosine rule, you can chuck this triangle into half. And since this is again, the only reason you can do this is because we know that this triangle is isosceles, because A and B have the same magnitude. So you can assume that on the right hand side here, so this will be exactly pi over 2. And you can just say that cos of 20 divided by A, and then you can just solve this. So you can just solve this one as you normally would with the cosine rule, and you should get the exact same answer. So again, both of these methods rely on the assumption that A and B are the same, which we did show was exactly the case in the previous question. So 133 meters per second is our final answer for this question, and this is an excellence level question if you can get the correct answer. So to get a merit, you can have up to one error for a merit. So merit is 1 error, and for an achieved correct calculation. Okay, so initial momentum is calculated. That is an achieved there. Okay. All right, so question 3, a pendulum on Mars. Some space explorers on Mars want to check that their electronic timers are functioning correctly. They make a simple pendulum using a large rock of mass 2.3 kilogram, and they tie it to a wire. The distance from the center of mass of the rock to the fixing point is 1.83 meters. On Mars, the gravitational field strength is 3.72 newtons per kilogram. Show that the period is 4.41. So for these types of questions, it's really just a plug and chug. So we know that T equals to 2 pi times of square root of L over G for a pendulum. So T equals to 2 pi square root of 1.83 divided by, not 9.81, be careful, it's 3.72. And if we plug that into the calculator, that should give us 4.406 seconds, which is 4.41 seconds, 3SF. And this is a achieved level question. So just a plug and chug, relatively simple, nothing much to talk about there. So they set the pendulum oscillating by releasing the pendulum bob 0.3 meters away from the rest position. At the same moment, they start a timer. Determine the position of the pendulum bob from its release point 2 seconds after it's released. Use the space above to draw a phasor diagram to help in your calculation. Okay, so for this question, since our release position is from the maximum amplitude, the maximum amplitude of 0.3, so we're starting somewhere here. And since we're starting at the maximum, that means we should use y equals to a times of cos. If we were starting at the equilibrium position, then you will be using y equals to a times sine omega times t. But however, we're starting at the maximum, so therefore we're using y equals to a times cos times omega times t. Alright, so we're trying to find out the position, and we know the amplitude is 0.3. So that's why the amplitude as in the maximum displacement from the equilibrium is 0.3 meters. And we need to find omega, which is 2 pi times of f, and that should be time period. Period is equal to period is equal to 4.41. So therefore, omega equals to 2 pi over t, which is 2 pi over 4.41. So in this case, we know y equals to a times of cos of 2 pi over 4.41 times of the time, which is 2 seconds. And a is 0.3, so just plug this one in. And we should get an answer of negative 0.288 meters. And be careful when you're working with simple harmonic motion, all of the calculations are in radians. So make sure, so that's what I was saying before, after you do the momentum, you do need to make sure that you set your calculator back to radians, okay? So negative 0.288, what does that mean? So in this case, we've considered this displacement here to be positive. So on this right-hand side here, the release point, we're considering it to be positive, 0.3. And that's because we're starting with the displacement is equal to a times cos omega t. So just as an experiment, we can just to visualize what's going on, we can just plug in time equals to 0. So cos of 0 is 1. And 1 times the amplitude is 0.3. So when we first release the bob, we should be getting an amplitude of, or displacement rather, of 0.3. And we consider this as being positive 0.3. So therefore, the release position we consider as positive. So therefore, if we get a negative answer, this indicates that the bob is actually on the other side. So somewhere here. That's a bit too far, but you get what I mean. I'll probably do a better drawing than that. So bob is probably somewhere here, which is 0.288 meters on this side. And notice if you do decide to use y equals to negative a times cos omega t, that's also a valid approach. So in this case, you'll be considering the displacement to the right, so the release position, to have a negative displacement, and therefore on the left-hand side, it will be a positive displacement. So in this case, if you use y equals to negative a times cos omega t, you will get the answer of positive 0.288 meters. But in that context, it will mean the exact same thing in terms of context. So the context will still be the pendulum is 0.288 meters on the other side of the release position. So just keep that one in mind. So that's how you would interpret your answer. So the negative just means it's on the other side in this case. And I want you to find the position of the pendulum bob from its release point 2 seconds after it's released. So from the release point, as we mentioned above, it's actually 0.288 plus 0.3. Okay, so it's on the other side. So that's 0.588. Okay, cool. And that's our final answer for this question. And it's actually an excellence level question if you can get the correct answer. And if you can get a correct x, so correct of negative 0.288 meters, that's a merit. And if you can get the correct angular velocity here, that's a achieved. All right, let's go to question C. The amplitude of the pendulum decreases from 0.3 to 0.2. So explain why the period of the pendulum remains unchanged. So for these types of questions, you can justify it like logically. So you can either do logical explanation or like physical explanations, logical explain, or you can just justify with formulae, and both are generally okay, but we'll cover both of them for better understanding. So you can justify from the formula. So if we justify from the formula, it's actually really simple. So we say T equals to 2 pi L over G. We don't really see amplitude in this equation at all, so therefore amplitude does not affect period. Okay, so for more holistic understanding, so in terms of the physics principles behind it, we know for simple harmonic motion, we know that for simple harmonic motion, we know that displacement, not displacement. Sorry, apologies. So for simple harmonic motion, the acceleration is proportional to the displacement from the equilibrium position and opposite direction. So acceleration proportional to displacement from the equilibrium, and in the opposite direction. When I say opposite direction, I mean like towards the equilibrium. Okay, so therefore, displacement is lower. So basically, the maximum amplitude is lower, so the distance traveled is smaller. But acceleration is also smaller. So acceleration also smaller since it is smaller displacement. So acceleration also smaller. And these factors directly mitigate each other. So they hence no change to period. So that would be your physical explanation for this question. So something along those lines there. And this is a merit level question. And you can actually justify using the equation or like using physical reasoning. So both are actually accepted. But if you do have time in the exam, I do recommend you do write both, because sometimes they do want you to write, like they do want a cohesive explanation. So I do recommend, if you do have time in the exam, to just write out both of those explanations. Calculate the total energy lost when the amplitude decreases from 0.3 meters to 0.2 meters. So we can begin the answer by calculating the maximum velocity of the bob for the initial and the final amplitude. Okay, so the maximum velocity, so if we just look at any arbitrary velocity, so v equals to this or v equals to, we know that cos of x is strictly between 1 and 0, sine of x is also strictly between 1 and 0. So therefore the largest value of sine x and cos x is 1, so that's the maximum value. So therefore the max, v max, is therefore just the amplitude times the angular velocity. So in this case, so for the initially, v max is equal to 0.3 times of the period, 2 pi over the period, so that's equal to 0.429 meters per second, and this energy is equal to half mv squared. It's equal to half times of the mass, which is 2.3 kilograms, so half times of 2.3 times of 0.429 squared, which is equal to 0.212 joules. So after we have Vmax is equal to the amplitude times the angular velocity, which is now it's 0.2 multiplied by 2 pi over 4.41, and that is equal to 0.286 meters per second. and therefore the energy is half mv squared is equal to half times 2.3 times 0.286 squared, and that is equal to 0.0941 joules. So therefore the change in energy is equal to the initial minus, the final minus the initial. So this will be 212. Sorry. So the change in energy is, and that's equal to 0.118. So therefore, lost 0.118 joules. So that's the answer for this question, and that will be a merit level question if you can get this correct. And to get an achieved, if you can do one correct calculation with V max equals to amplitude times angular velocity, so in this step here, or this step, this step here, that's an achieved. And that's it for this paper. And I hope you enjoyed, and I hope to see you all in the next one.